Hi, this is lecture 2 of MT 2223, lecture 2. So, in the previous session what we have seen is the structure of R, the first layer of description for R. What was that? R came with the following data, I don't it correctly. R came with the following data. There are two special elements 0 and 1, they are not same, the 0 is not equal to 1. I am saying two elements, so they should be different. So 0 is an element of R, 1 is an element of R, then there is a addition map R plus R to R, then there is a multiplication map A comma B to AB, then there is additive inverse and multiplicative inverse. These are the data that comes with R, the first layer of description. Then we have seen that starting with the element 1 belongs to R, we produce the set n, the set of natural numbers 1, 2, 3, so on. Then using the additive inverse structure of R, for 1 belongs to R, there is minus 1 also should be in R, for 2 there is minus 2, for 3 there is minus 3. So we have combined, we have taken the union of all these elements, minus 1, minus 2, minus 3, so on. Then we took union with the set of natural numbers. Then we have mentioned that it is denoted by Z, the set of integers. Then what we have done is, now we have considered the multiplicative inverse map. For every element A belongs to R, that is non-zero, we have 1 by A, an element of R. So in particular for every element in Z that is non-zero, there is 1 by the multiplicative inverse. So then we have considered that also, 1 by A for A belongs to Z minus 0. We have combined this with the previous with the set of integers. So now we have integers union 1 by A for A non-zero in integers. Then what we have said is we did not use the multiplication map anywhere till now. So now we will use multiplication map. So for an element A belongs to Z and 1 by B belongs to 1 by B, for B belongs to Z, we can take the product A dot 1 by B, we are writing it as A by B. So now this gives another set A by B, for A belongs to Z, B belongs to Z minus 0. So this we are calling a set of rational numbers, we are denoting that by Q. So that is the description that we have mentioned yesterday. Then we introduced to talk about the second layer of description for R, we said we need the notion of what is called order on a set. Let me write down that. So the second layer of description is S subset of R plus R. We are saying this is an order. Then we stopped at the place where we said the compatibility of the order with the field structure. So this data, whatever I have mentioned here, this data is what I am calling as the field structure of R. Now we will describe what do you mean by compatibility of the order with the field structure. So I will write down the conditions. So the first condition is about the addition. Suppose we have this, maybe I will fix some notation first. For an element A comma B belongs to S, we will write down this notation A less than or equal to B. Ideally you should be writing S here. See, I mean to remember that this order is with respect to S, the one yes, this yes. But I said in the previous lectures also, we do not write so many details partially because of laziness. So we will simply write A less than or equal to B to mean that we are only dealing with the one fixed order S belongs to R cross R. So A less than or equal to B should just mean A comma B belongs to S. So this is one notation. Then if A comma B belongs to S and I know that A is not equal to B, then we will simply write A less than B. So A less than or equal to B means A comma B belongs to S, A less than B means A comma B belongs to S and A is not equal to B. So this is one notational clarification. Now let us come to the compatibility condition that we mentioned. Compatibility condition. So the first condition is about the multiplication property. So addition property. Suppose A less than or equal to B, which means what? A comma B is an element of S, and then we have some element C belongs to R. Then the first compatibility condition is A plus B is less than or equal to A plus C less than or equal to B plus C. Well, this write down. So A less than or equal to B and C belongs to R implies A plus C less than or equal to B plus C, which means what? If I am taking two elements A and B with this order, for any element C, if I add in the C on both sides, the condition still remains true, that A plus C is still less than B plus C. That is the first condition. For the second condition, again I am starting with A less than or equal to B only, and C belongs to R. See, we mentioned about addition here, now we will do the multiplication part. C belongs to R, one more condition is there, that C should be greater than or equal to 0. So this is an extra condition that they are asking. So if C is greater than or equal to 0, then we have AC less than or equal to BC. So these are the two compatibility conditions that they are asking for us to satisfy. R with this structure is called the field structure of R. Then if it is if R has an order with this compatibility condition, then that is called ordered field. The name may not be relevant here, but it is called an ordered field. Okay. Now one should ask a question here. We mentioned that the order we want to be compatible with the whole structure of the field structure of R, but we only mentioned about only two things. One is addition, one is multiplication. So what about the remaining things? Right, there is so much other structure. So let me write down. So 0, it was part of the data because we mentioned about 0 here, right. So compatibility condition 0 is playing some role, fair enough. 1 is not playing any role, right. Nothing in these two conditions, there is no mention of 1. So I do not know what happens to 1, we will see. Now about addition. For addition also, it is only partially, we are taking some element, some relation A less than or equal to B. Then for an element C belongs to R, only for a single element we are adding the single element on both sides, right. So this I am considering as a partial compatibility, in the sense, suppose, see, I want to do something like this, A less than or equal to B and C less than or equal to D. This is not saying anything about A plus C and B plus D, right. This is what I would like to think about, but this condition does not say anything about that. If I take some element, some situation like this, for every element we have this property. This does not say anything about adding two elements simultaneously. This is not saying anything about that. So we will see this also. So this is partially involved in the compatibility condition, but not fully. So we will see that also. Now this multiplication, this is also partially. Why? Because when I am saying about this situation, AC less than or equal to BC, we are asking this extra condition, that 0 less than or equal to C. Now one obvious question to ask is, okay, what happens if I take C is less than or equal to 0? Does it say anything about AC and BC? AC and BC, is it of this form, or do we have this situation, AC less than or equal to BC or AC greater than or equal to BC? So this is not part of the compatibility condition. So who will tell me what to do here? So this we will see. Now additive inverse, absolutely no condition is mentioned here, right. You know, at least I cannot see. Suppose A belongs to R with A is greater than or equal to 0, these two conditions does not say anything about minus A being greater than or equal to 0 or less than or equal to 0 or anything like that. So we will see that also. So, this is absolutely nothing, and similarly multiplicative also inverse. So, suppose I know something about A, I do not know whether it implies anything about 1 by A or not, it is not very clear. So, we need to work on, so we will at least have to ask 5 questions. One is about the element 1, the other is about complete compatibility, I mean some compatibility, extra compatibility between the addition situation, and about multiplication, and these two are separate questions. I mean, they do not say anything about additive inverse, multiplicative inverse. So, what do we do? So, we will try to answer one by one and see how much we will succeed in doing that. Okay, what was the first question? It is about the element 1. 1 is an element of R. Nobody told me whether 1 is greater than or equal to 0 or 1 is less than or equal to 0, right. When I say that S is a total order, I think I said, if I did not say, I am saying now, this S is total order, which means what? Any two elements can be comparable. For an element A comma B belongs to A and B in R, either A comma B belongs to S or B comma A belongs to S. So, this is what we mean when I say that S is of total order. In that case, what we are doing, we are starting with the element 1 belongs to 0, 1 belongs to R, we have other special element 0, right, 0 is an element of R. Now, one can ask whether either this is true or this is true, but 1 is not equal to 0, that is the starting point description of R, right, I mentioned here. These are two different elements of R. So, this equality is not going to happen, it is only it's a strict equality, strict inequality. Either we have this situation or we have this situation. So, how do we see what is correct? Let us start with some assumption. Suppose 1 is less than or equal to 0. Suppose 1 is less than 0, then what happens? The first condition of the compatibility condition says I can add any element, the equality remains same. Let us do it here. So, 1 is less than 0 is assumption. If this is true, then if I add an element on both sides, the same element, the inequality should remain same. So, now I am adding what? Minus 1 on both sides, right. Now, because minus 1 is additive inverse of 1, this side we are getting as 0, this side we are getting as simply minus 1, I will write down that minus 1. So, if I assume 1 is less than 0, this is suggesting that 0 should be greater than or equal to minus 1. Now, what? Let us use the second condition. What does it say? If I am starting with this some relation like this, and if I know C is positive, these two should imply AC is less than or equal to BC. Let us do the same thing for here, for this situation. 0 less than minus 1, see, treat this as same thing as this. Now, again 0 less than minus 1, it looks like I am writing same thing twice, but this first thing is about this, the second thing is about this. So, what does this say? This says if I multiply by minus 1 on both sides, this inequality should remain the same, there should not be any difference. So, what do we have? 0 times minus 1 is less than minus 1 times minus 1, right. Now, this is same thing as saying this is same thing as 0, right, that is the property of the 0 element. If we multiply 0 by any element, I am supposed to get 0. So, 0 is less than minus 1 times minus 1. I did not say anything about this, right. How do I know minus 1? I do not even know what this means. Minus 1 times minus 1 means what? That you will see in the assignment. Just with the previous description of R, the field structure, you can prove that minus 1 times minus 1 is 1. This you will see as an assignment problem. So, for the additive inverse minus 1 of the element 1, this product is same thing as 1, that you will see in the assignment. So what did we get? Assuming 1 is less than 0, we got 0 less than 1. So this is a contradiction. Contradiction to the assumption that 1 is, let's put it. Okay. So this situation is, this assumption is wrong if I want it to be compatible with these two conditions or the field structure of R. So this is not going to, this is not true, and what we have is just this. So just by considering the compatibility condition of S, we proved that 1 should be positive, should be treated as positive. Okay, that answers this question, right? That is what we asked here. So what do we say about minus the 1? Now let us think about the addition. What is the problem? The only condition that they have given is, suppose A less than or equal to B and C is an element of R. This says A plus C is less than or equal to B plus C. Now I want to see, suppose A less than or equal to B and C less than or equal to D, can I say anything about A plus C and B plus D? What relation can we expect here, or is there any relation between these two? So what we do is, we will try to do step by step. See, once we have this condition, for any element C we have this. In particular for this C, we can write the same thing, right? So we will write down that. So A plus C is less than or equal to B plus C for this C that I have chosen here, right? This is given, C and D are given, and they are said, and we have been told that this is the relation between C and D. Now let us take this as the starting point, and so for C less than or equal to D, for any arbitrary element, say R, we should have this same thing, right? For C less than or equal to D, this is true for every R. In particular, for R is equal to B, we have this condition, which means what? B plus C less than or equal to B plus D, right? I am doing the same thing twice. Starting with A less than or equal to B, I took this element C and I have written this. Starting with C less than or equal to D, I took this element and I have written this. Now what does these two conditions combinedly say? Transitivity of the order says I can really ignore this and simply arrive at this point. So what does this say? For any pair of elements A and B of this form, C and D of this form, we have this condition. So whatever I said about addition being partial, it's not really partial, it is fine, not very bad. Now let us do the additive inverse part. In the sense, we will ask the following question: suppose somebody tells me that A is positive, does it imply anything about minus A? Right? That is the question that we want to ask. That if somebody tells me that A is positive, do I know for sure anything about minus A? Is it negative or is it positive? That is the question that we want to ask. Okay, let us just start with A positive. What is the first condition says? If I have this kind of situation, we will write down in a different way, 0 less than A. I mean this that's what the usual notation, right? A less than or equal to B, that's what you are using here. So the first condition says, if I add a particular element on both sides of the inequality, the inequality remains same. That is the first condition. So we will do it here. So if I add a particular element on both sides of this inequality, 0 and A, then this inequality should remain same. In the sense, let me add minus A both sides, less than A plus minus A, this should remain same. That's what the first condition says. Now what is A plus minus A? This is something as 0, right? That is the alternate inverse. So if I add A and minus A, I am supposed to get 0. So let me remove that element, this thing, and just keep 0. What is minus A plus 0? It is simply minus A. So I am removing that also and writing minus A. So if I assume A is greater than 0, this implies minus A is less than 0. So what do we observe from here? Even though they did not say anything about alternate inverse, just this condition along with the second condition confirm something about alternate inverse, whatever we have mentioned just now. A times minus A, A is positive implies minus A is negative. Okay. Oh, we missed this multiplication part. Let us do that also. So what is it? If somebody tells me A is less than or equal to B and C is positive, I will write C is positive, then I know for sure that AC is less than or equal to BC. So this is the second condition about multiplication. Now what we are asking is, okay, what can we say about AC and BC if I know C is less than or equal to 0, right? That is the question that we want to answer. And how do we do that? That if an element is positive, if A is positive, this implies minus A is negative. Similarly, if A is negative, the same observation as before confirm that minus A is positive. So we will use this observation in the previous in this situation. So C is less than or equal to 0, C is less than 0, we can ignore the 0 situation, C being 0, we are ignoring that. So C is negative, C is less than 0, then what can we say about minus C? This is positive. So now what we do is A less than or equal to B and minus C is greater than 0, this implies A times minus C is less than or equal to B times minus C. So this we are writing as this A times minus C, same thing as minus of AC. This we are writing as minus of BC. And how do I know this? Who said A times minus C is same thing as minus AC? Just assuming the properties of R, the structure of R, you need to prove that for any two elements A and C, A and minus C combinedly gives this element, right? Yeah. So this is the situation. Now what do we have? We have minus AC less than or equal to minus BC. Now what we do is we will just add the same element both sides, right? That's what the first condition says. If there is some order, if I add an element on both sides, the inequality remains same. Minus AC less than or equal to minus BC, we are adding AC on both sides. So this is 0, less than or equal to minus BC. Now what we are doing, we are adding BC on both sides. So this is plus BC plus BC. Because BC is alternate inverse of minus BC, this is gone and this plus sign also. So BC plus 0 is simply BC, so we can just remove this also. So what do we have? If C is negative, that's what I have started with, right? If C is negative and A is less than or equal to B, then the inclusion is the relation is reversed. Let me write down that here. A less than or equal to B and C is negative, this implies AC is, this implies BC is less than or equal to AC. If C is positive, this remains same, that AC is less than or equal to BC, C is negative, this is changed. So that is about this multiplication. Now what is remaining? Multiplicate inverse, we will do that also. So now what is the question? Suppose somebody tells me A is positive, what can we say about the multiplicate inverse 1 by A? Is it positive? Is it negative? Is it positive? What is it? Again, suppose let us assume that this is the situation. What is it? 1 by A is less than 0. So 1 by A is less than 0. Then what we said in the as the compatibility condition of order with the field structure, if I am starting with a positive element, if I multiply them both sides of some relation, the order should not change. In the sense, if I multiply by A on both sides of this order, I still have the same inequality. By the way, what is this? A dot 1 by A is simply 1 and 0 dot A is simply 0, right. If I assume 1 by A is less than 0, this is suggesting me that 1 is less than 0, but as I said before, 1 is positive. So this is contradiction. So this assumption is wrong. So if A is positive, this should imply 1 by A is positive. So this is the compatibility condition between the compatibility condition between order and the field structure of R is giving us so many things. It looks like it is only dealing with, see, it looks like it is only dealing with addition and multiplication partially, but no, it is saying many things about one, this full description of addition and also multiplication, additive inverse, multiplicate inverse. So it looks like only two conditions, but they are actually dealing with the whole the full structure of R, the full field structure of R. Nice. So this is about compatibility condition between order and the field structure. Now this is, I only mentioned I only asked a few questions, so these are the answers for that. In the assignment, I'll ask you something. I'll ask you to prove some other equations, some other relations also, some other observations. You can try to prove by yourself. So that's about the compatibility condition. Now, so now what we have the setup that we want to work with is the set R with the field structure. I am not going to write down that plus minus again and again. Field structure and the order. Order, as I said, is a total order, subset of R cross R, and what we said is these two are compatible. So this is what the two layered description of R that we are dealing with. So I said in the last lecture that we are, for us, R comes with two layers of description. One is field structure, one is order structure, and these two are compatible. In the sense that I mentioned just now, I mentioned about spent some 40 minutes about trying to explain the compatibility, and that's what we have. The situation is here. Now one can ask the following question. Okay, assuming that R is a field, we mentioned about this natural numbers n, z, q, and something else. Now what extra information do we get by assuming that there is an order? This is a fair question. You will not get anything new. If I assume that order is special, see, not just compatibility with the field structure. If I assume order is special, we will get some extra elements from so we want this order to be special. What is speciality? It goes by the name of what is called completeness axiom. Completeness of order. So what is so this condition says what? Suppose I take two subsets of R, x and y are subsets of R, and if I know that for every x belongs to x and y belongs to y, we have x less than or equal to y. So this is the starting condition that I am assuming. X and y are two subsets of R with the condition that for every x belongs to x and y belongs to y, we have the condition x less than or equal to y. The completeness says there exists an element S belongs to R such that x is less than or equal to S for every x belongs to x. Similarly, y is less than similarly S is less than or equal to y for every y belongs to y. So this is the completeness of order. These completeness of order assure some extra structure, some extra information about elements of R. So maybe in the next lecture I will explain something more about this completeness, and this is where we stop about this session about the description of R. So this is the full description, the two layered description of R. First is it's a field. Field means the structure that we have mentioned here. Right. So it's a field. There is an order, and it is compatible with the field structure, and it is complete. What is complete? The whatever I have written here. For any two subsets of R, if we have this condition x less than or equal to y for every x belongs to x and y belongs to y, then there is an element S belongs to R such that S is of this form x less than or equal to S for every x belongs to x, and S is less than or equal to y for every y belongs to y. So this is the situation of, this is the completeness assumption that we are asking for the order. With this structure, the description of R is complete, not a pun. This complete is that complete. So this is the complete description of R. Now in the next session what we will see is, we will give some meaning for these symbols, right. I mentioned in the last lecture also, but I am saying again. So in the next session, that is possibly tomorrow, we will try to see what this means, and we will try to see whether this belongs to R, and maybe something more. That is all for today's session.